Welcome to this explainer. Okay, today we are going to do something extremely practical. We're going to build the ultimate study guide to help you completely master the fundamental physical properties of materials. By the time we wrap up here, you're going to have a crystal clear mental framework for classifying literally the very substance of the world around us.
But before we dive into the weeds, let's do a quick exercise. Take a second and just look around the room you're sitting in right now. Can you spot at least 5 different metals? Maybe there's a door handle, a straight paperclip on your desk, the frame of the chair you're in, or maybe some jewelry you're wearing. Now ask yourself, how do you actually know those objects are made of metal? What is it about their physical nature that totally gives them away? I want you to keep those thoughts in the back of your mind as we move forward.
So here is our game plan for today's explainer. We'll start with the material world, move into mighty metals and their real-world uses, contrast those with the complete opposites in non-metals, and finally, we'll bring it all together to build that ultimate study guide. Let's get started.
Part 1. The material world.
Moving right into Part 2, mighty metals and their key properties.
When you think of the heavyweights of the material world, you probably picture sheer strength, right? And generally speaking, you'd be spot on. Metals are incredibly strong, tough, and they have this beautiful luster, meaning they are extremely shiny when freshly cut or polished. They also boast really high melting and boiling points. Basically, it takes a massive amount of heat to melt them. Though there is one fascinating exception you should know: mercury. It's actually the only metal that is liquid at room temperature. On top of that, metals are fantastic conductors of both heat and electricity. Oh, and finally, some of them, specifically iron, steel, nickel, and cobalt, are naturally magnetic.
Now, let's add a few crucial vocabulary words to your arsenal for this study guide. First up is malleable. This concept brilliantly explains why metals are absolutely everywhere in construction and manufacturing. Being malleable just means the material can be bent and forcefully hammered into a totally new shape without shattering. Think about it. If you drop a heavy block of iron, it doesn't crack into a million pieces like glass, right? It just absorbs the impact.
Next up is ductile. This means a material can be drawn or stretched out into long, thin wires. This specific physical property is exactly why we're able to string giant power lines all the way across the country and snake those tiny little cables through the walls of our homes.
And our third big vocab word is sonorous. This means it makes a distinct ringing sound, kind of like a bell or a cymbal when it's hit. Now sure, a glass bottle might make a ringing sound too, but true sonorous resonance? That's a classic hallmark of metals. If you tap a piece of wood, you get a dull thud, but tap a metal pipe and it rings.
All right, Part 3. Metals in action.
Let's see how these properties dictate how we actually use these things in the real world. Think about the sheer strength and toughness of iron. It's immensely strong and malleable, making it the perfect foundational material for building massive weight-bearing structures like bridges. But then, compare that to gold. We don't use gold for its structural strength. We use it because it is highly malleable, has an incredibly shiny luster, and is quite rare. All of that makes it absolutely perfect for beautiful, expensive jewelry.
Then there's copper, which beautifully showcases the property of ductility. Copper is used globally for electrical wiring because it gives us 2 vital traits at the exact same time. It is an exceptional conductor of electrical currents, and it's flexible enough to be spooled, bent, and routed absolutely anywhere we need power to go.
Let's look at another everyday example: steel. You know when you touch a cold piece of metal and it actually feels really cold to the touch? Well, that's because it is rapidly conducting the heat energy directly away from your hand. That exact same property is what makes steel so useful for cooking pans. It takes the heat from the stove and conducts it super efficiently and evenly right into your food. Switching gears now to Part 4, non-metals, the complete opposites.
If metals are the heavyweights, non-metals are kind of the underdogs. But honestly, they are just as vital. The absolute easiest way to learn them for your study guide is to view them as direct physical opposites to metals. Non-metals generally look dull. They lack that luster and just don't reflect light well. They are extremely poor conductors of both heat and electricity. They definitely aren't as hard-wearing as metals either. And while some are solids, a ton of them are actually gases at room temperature, which tells us they naturally have very low melting and boiling points.
Time for some non-metal vocabulary. If a non-metal is solid, it's almost always what we call brittle. This means it might shatter or crack super easily if you drop it or hit it. Remember how we said metals are malleable and can be hammered into shape? Brittle nonmetals are the exact opposite. Hit them with a hammer and they're just going to break into pieces.
So that brings us to a massive concept: insulators. Because nonmetals are incredibly poor conductors, they act as insulators. And listen, this isn't a weakness, it's practically a superpower. We specifically rely on nonmetals to make the protective coverings for our electrical plugs and cables and for the handles of those hot steel cooking pans we talked about earlier. Their inability to conduct is exactly what keeps us safe from burns and electric shocks.
Part 5. Everyday nonmetals.
Because of their extremely diverse chemical reactions, nonmetals pop up in ways you might totally not expect. Take sulfur, for instance. It's a yellow, nonmetal solid that is actually added to rubber to make it hard and durable. And then you have helium. It's a nonmetal gas that's literally lighter than air, which is exactly the property we exploit to make balloons float.
Here are two more vital nonmetals in action. Pure oxygen is obviously essential for human life and is utilized constantly in hospitals for people experiencing breathing difficulties. And chlorine, which is a nonmetal gas, can be dissolved in water to effectively kill harmful bacteria. That's exactly why we add it to our swimming pools to keep them clean and safe.
Finally, Part 6, the ultimate study guide.
Let's consolidate everything we've talked about into a rapid-fire comparison. Metals have a shiny luster. Nonmetals are dull. Metals are malleable and won't shatter. Solid nonmetals are brittle and absolutely will shatter. Metals are excellent conductors of energy. Nonmetals are insulators that block that energy right in its tracks.
Okay, here it is, your definitive study guide table. I highly recommend pausing for just a second and taking a mental snapshot of this. It perfectly summarizes the head-to-head physical differences we've explored today. Just look at the flow. Luster goes from shiny over to dull, durability goes from strong, malleable, and ductile all the way over to brittle, conductivity drops from good down to poor, sound shifts from a sonorous ring to a dull thud, and the melting points go from incredibly high down to very low.
And to totally round out your study guide, here is a consolidated list of the real-world examples we pulled directly from the source material today. For metals, we covered iron for bridges, gold for jewelry, ductile copper, liquid mercury, heat-conducting steel, and magnetic nickel and cobalt. For nonmetals, we saw sulfur for rubber, floating helium, breathable oxygen, bacteria-killing chlorine, as well as carbon, which we use to purify water, and silicon, which is literally essential for making the computer chips inside your devices.
So you now have a really solid, functional grasp of the physical properties that separate these materials. But honestly, physical properties are only half the story. There is a deep, underlying chemistry that dictates all of this. So I want to leave you with one final provocative question straight from our source material. Where exactly are these metals and nonmetals found in the periodic table? Like, what patterns exist there that create these incredibly distinct materials? I highly encourage you to look that up and continue your learning journey. Thank you so much for joining me on this explainer, and I'll catch you next time.